we're going to see now the basic concepts of bone graft modeling, and we'll study the basic elements and introduce them and introduce the kind of variables that we use. And then later on, we'll look at the individual constitutive relationships and towards the also building a model for simulation. So in here, we're going to say, okay, you have these systems in here that have different variables in different energy domains. Like in this case, you have a mass which has a force applied on it, and it's in here, and the mass. The way we measure power on this kind of system is multiplying the force times the velocity, right? For this other one, on the electrical side, we multiply the voltage times the current. So one question that comes to mind immediately after doing these two systems, you would say, isn't it true, or would it be possible that somehow the variable f is related to the v variable, or the to the big V? I mean, this small v is for velocity, would be related to the current, or is there a relationship? Let's take a look at the next one before we answer that question. Do you see in the rotational system that you're seeing here, the input to the system is a torque and the response is an angular velocity. So the torque and angular velocity are together in this case for this. And on this one, which is the hydraulic system, you have um, the pressure and the volume flow rate. Those are the variables. Now, I mentioned to you that Professor Painter, who invented this technology of bone grafts in the 50s, had the idea that systems in nature interact with similar variables, but similar variables, what I mean by types of variables, similar type of variables, but of course, because we do it in different energy domains, the units are very different. That's why you can measure the force in newtons on a mechanical system, but you will measure the voltage in volts on an electrical system. But what, what Painter is saying is this family of variables called force for this system, called the force for the system, called voltage for this other, called torque for this other system, and this one called pressure. Those are in the same family of variables. But in being in the same family of variables implies also that the volume flow rate, the current here, the velocity, and the angular velocity suggests they also belong to another family, different type of variable. So what Painter is saying is that systems of many different energy domains are, they talk to each other. They the power induced in one of these systems is equal to the effort and the flow. So effort is going to become the synonymous of force, of torque, or voltage, or pressure. And this variable flow, which we'll call it, the effort we'll call it E, the flow we'll call it F. But if you have this, the velocity, the current, and this volume flow rate, this is what you have, the flow. So many systems, I would say all systems, can be analyzed in this principle. Power is effort times flow. Let's go up a little bit more. If we look at the specifics of this, you know that the efforts, we could classify them as a little table in there: force, voltage, torque, and pressure. The flows on the other side are velocity, current, angular velocity, and volume flow rate. So there you have all the effort variables. When we say effort E, it could mean any of those. When you say flow F, it could mean any of those. So in this particular case, the effort and the flows, we are going to look at use it in a way that we can actually generalize things. Here I'm gonna write it down in here. This is gonna be my effort variable. I'm gonna call it E. This force, and the F is gonna be F. And then we have these variables, you know, E and F, so far for the different things. So this we're gonna call it for flow, this for effort. Okay. If you relate the efforts and the flows, and you find the derivative of the effort, the not the derivative of the effort, the derivative of the momentum, or the derivative of the position, you're going to get these two other variables. One is P, the momentum variable, and Q, the position variable. So always when we work with this technology, we look at four variables: P and Q and E and F. Okay. And then we have a more detailed version of this for all the energy domains in there. You see how the effort and the flow are measured, and the displacement and the momentum. But these are the four basic variables that we use to interpret and get output and do all kinds of things with them for this system. So this is E. Okay. Okay, let's write it down what I was saying. This one in here, this is the effort E. This is the flow F. This is the displacement displacement, and then you have, this is the momentum P. So these are the so-called generalized variables. Generalized variables. So we're going to be using this notation for E and F, P, and Q. Okay, let's go on. Let's start assembling something here. This is, and at the same time, try to understand how these variables relate into the system. So one way that the bond graphs have been perfected is those who came after Professor Painter produced a simple notation called word bond graph. And what it is you list the different elements. As you can see there, they're listed in red. And in between the elements, you write the units that they interact with, like in this case, voltage and current, or you could have torque and the angular velocity. So when we put the symbols in there, like the ones on the bottom, you say battery, the motor, this is, we're starting, this is your starting motor that I used this morning. The battery gives a, puts out a voltage, and then the armature of the motor, current circulates in a magnetic field, resulting in a torque, and that's how your car starts. But the representation of that little system implies the use of these generalized variables. Like in this case, you have the bending. Here's, you have the battery, sorry. Put the voltage here, and then you have the motor, and then you have the torque and the angular velocity. This is called word bond graphs. Let's go to the next one. In here you have a car model, just on the engine and the clutch and the gearbox and the drive shaft and the two wheels in there. You see, but it is in words right there. But this topological representation you have the ability with this representation to do a more detailed model that you would do it with other methods. So in here you have the engine. Of course, it has an input in here, which is the throttle. The clutch also has a control position, and the gearbox also has a gearbox, for different speeds. And then later on over here is the differential, and then the wheels. So this is the model of an entire vehicle using the word bond graph concept. Now, let's talk about this interaction between the two elements. The interaction between the two elements always occurs through these two variables, the effort and the flow variable. So in this case, you see that A applies the effort to B, B reacts with F. In this other case up here to the right, that A applies to the B, and to B, and then you have that in this case the effort goes from B to A. So take a look at the one on the bottom in here. This is the picture on the right hand side, I mean on the left hand side, indicates that the output is coming out of A. Effort is coming out of A and flow goes into A. That's how you read this. The symbol that you see like that means this is the output and this is the input. And that's what you see in there. On the other hand, on the other side, is different. So I could actually make a little bit more comments in here to help you clarify this. See, so let's just let's see what happens. Yeah, here. See, now I can write on it. This thing in here, this is your output. And this is your input. Input. So output and now I was just doing a little dramatic explanation the other day. This is as if you have it your hand in there and push it towards this crossbar. So okay. So this is the block diagram representation of this. And this is the bond graph. Bond graph. All right. So let's go on. In order to do this, we need 9 elements. And we need to explain the constitutive laws of all those 9 elements, which we will do next.